So again, good morning. Thank you for having invited me to give this talk today. So we'll discuss about photodesorption from interstellar IS analogues. I will try to make a brief summary of what is currently known in terms of photodesorption yields, what we know about some mechanisms, and try to present some newest studies that we made relatively recently. So why photodesorption, and more generally, why are we interested in non-thermal desorption? Well, non-thermal desorption is a process which will be important mostly in the coldest part of the interstellar medium. For instance, in clouds, in the inner region, in the border region, also in protoplanetary disks, in which we know temperature can be quite low, sorry. It can go down to about 10K. And in this region, we know that the gas is primarily molecular, and its interaction with cold dust grain, which in fact results in the formation of molecular ices. And these molecular ices are in fact the main reservoir of molecule, except H2, of course. Of course, it's a very important phase to study because it will lock most of the molecular richness in this cold region. However, the molecular richness we can also see in the gas phase. We see a lot of simple molecule in the gas phase, but also we see, and it's more puzzling, the presence also of organic molecule in the gas. However, in this temperature regime, normally much of this material should be locked in the dust grains because of the temperature. And so if it should be depleted on grain, the question is, why can we observe this molecule at these abundances in the gas? And if we want to understand that, we have no other options than to consider that there are processes which are not thermal, which helps to take the molecule from the reservoir to the gas phase where we observe them. And this is typically the process of non-thermal desorption, which are here. And of course, this non-thermal desorption process are important, but if one wants to consider them, we have to know yields. This is the most important thing. If one wants to model these abundances, one has to know how much non-thermal desorption works. Also, I will discuss that a bit later. One has also to know what are the mechanisms involved in the non-thermal desorption, because it will impact somehow the way you will have to model this process. So, of course, there are many ways of non-thermal desorption. You can have chemical desorption, you can have desorption induced by shock between grains, you can have desorption induced by shock of cosmic rays, for instance. And I will more focus on the photon-induced desorption. That means the desorption which is induced by the UV or even X-ray radiation. And this is usually referred to as photodesorption. So why photodesorption? When it's in fact, it's a process which has been considered for a long time as being an efficient or potentially efficient way to maintain a certain budget of gaseous molecule for them to observe. And of course, over the years, this has motivated a lot of laboratory works in order to measure this photodesorption process and to extract some yields from these experiments. Most of the time, the idea to study it experimentally is quite easy. You prepare in a vacuum chamber some molecular ices, which you want to study on a cold substrate at very low temperature, and then you will send UV photons on them. But in fact, you've got many ways of sending UV photons on molecular ices. Most of the time, people use broad spectrum hydrogen discharge lamps, which are relatively easy to use. And they provide a broad spectrum with a strong contribution at the Lyman alpha. But unfortunately, these are also source for which you cannot really control, in fact, the energy of the photon you send. So you can say that this kind of spectrum you can have with a lamp, which you can see here with a strong contribution as a Lyman alpha, could be a good representative of secondary UV photons that you can find, for instance, in clouds. But if you're going to the age region, like in PDR, for instance, normally the spectrum should be different because it would more be like an ISRF attenuated the more you go into the cloud, for instance. Also, the problem of this kind of source is that you've got a cutoff at 10.5 eV, so you don't have any impact on possible more energetic photon on the process, and the flux is usually quite high. Other people also use laser sources. Laser sources are very powerful because it's pulsed source, and with pulsed source, you can do some time resolved measurements. And this is very helpful to understand the mechanism of the desorption. Unfortunately, from laser sources, it's extremely difficult to get quantitative yields because it's very difficult to know the exact flux because of instability pulse to pulse, for instance. And also, it's extremely difficult to generate UV photons which are violet enough to be really relevant in terms of the interstellar medium. Finally, and this is a bit of specialty, we can also study the photodesorption by using monochromatic light that you can very easily tune over a very wide range of energy. And this is typically the case of the output of synchrotron radiation. It's a very powerful technique because the light is monochromatic. You've got a full control of its energy. You can go to very wide range. You can even go to the soft X-ray domain. There are actually a lot of work which has been done this last year on this specific case. The only issue is everything but tabletop. Access to synchrotron is limited. Experiments are easy to do. At maximum, you can have 1 week. If you're extremely lucky, 2 weeks a year to do this experiment. So you have to be efficient in this case. So with all these kind of experiments, in fact, there are many molecules which have been studied in terms of photodesorption. So it's probably not exhaustive list. All the studies which are here are studies which in fact give yields. They recommend some yields. There are many more studies dealing with the mechanism, for instance, but I won't discuss them. And in terms of, let's say, simple molecules, there have been many systems that has been studied over the year, CO, water, CO2, N2, and so on. But what I would like to stress here is first, most of the time, the yields that are extracted were extracted from pure ICs. So for N2, the yields we have is from pure N2 ice, for instance, pure NH3 ice, pure O2 ice, pure NO ice, and so on. Second, and it's also important to stress that, if you shine light on a molecular ice, it's not only the molecules that you've deposited originally, which is dissolving. There are many things that can happen. You can have photodissociation, you can have photochemistry, and which means that just in the case of water, for instance, you will have photodisruption yield of water, but also OH, also O2, H2, and it's the same for a big collection of molecules which are here. Third thing that we can say, there were many studies on this molecule, but in fact, there were many studies which were made with very different experimental conditions. Here, for instance, in blue, these are all the studies which were made with a broadband lamp. In red, these are studies which were made with synchrotron light, so monochromatic light. Also, in all these studies, the photon flux vary quite a lot over several orders of magnitude. And as Antoine discussed a bit earlier this morning, this can actually change things in terms of absolute yields. So what are the consequences of that? Well, the consequence is that sometimes the yields that one can find in literature are varying. Not a lot, but they do vary. So it makes things extremely difficult at some point for modelers, for instance. Okay, what kind of value can I take? So we can understand a bit more. So this is everything concerning yields, but in fact, over the years, we also obtained information on how this works in terms of mechanisms. First of all, photodisruption yields depend on the molecule. This is a very important thing. For instance, if you take pure CO, you can have yields from 10 to the minus 2, 10 to the minus 3. If you take formaldehyde, you will go down to 10 to the minus 4. If you consider water, you will have intermediate thing. So things are really varying from a system to another one. A second thing is that the yields actually depend on the photon energy. That's also an important point. For instance, here these are photon energy result, photodisruption yields that we have obtained. Here it's from a pure CO ice. Here it's from a pure CO2 ice. And if you see the energy structure of the yields, they are strongly, well, they are extremely different. And in fact, it depends on the absorption cross-section of the molecules that you're considering. For instance, here is that you can see that for CO2, if you just shine photon with energy below 10.5 eV, in fact, you miss the majority of the desorption phenomena. So this is basically what will happen if you use a broadband discharge lamp. Third, and it's another complication to understand what's going on, the yields depend on the composition of the ice. It is true for ice containing water. It is true for ice containing CO. And if I go back to the case of CO, we showed over the years that even from a pure CO ice, the mechanism occurs via a diet mechanism, which Antoine discussed a bit already, which pass by the excitation of a bulk located molecule, and somehow the energy is getting transferred to the surface and pops the molecule of the surface. This works for CO, but this works also if you make any other coadsorbate with CO. For instance, if you take another molecule like N2, methane, CO2, or even atoms like rare gas, this phenomenon, indirect phenomenon, is extremely efficient. But it's not always efficient. First, okay, this is indirect. It's nice, but it's really unclear how the energy is getting transferred. First, it's not working for all coadsorbates, which means that, in fact, well, we can measure that things are happening, we don't know really why. So if at some points one wants to give yields which are really relevant to multi-component ice, like the one we actually detect in the interstellar medium, one has to understand how such composition effects of indirect transfer actually occur for us to be able to predict relevant yields. And we are not very on this stage now. So how to model this, how to model the composition effect, where we have no choice but to know really on a microscopic scale how this process happens in this case of, let's say, simple molecular ices, and how that works. Well, we were not only studying simple molecules, there are also cones, which are very interesting. We actually detect them in the cold interstellar medium. Problem is when you look at the photodesorption studies that has been done, where before the, let's say, 2022, only methanol were studied. And if you consider the case of photodesorption of methanol, well, okay, data are scarce. We only know about methanol for cones. Second, as you see, because this kind of organic molecule breaks quite a lot, you will end up with a collection of molecules which will desorb. Some are stable molecules, some are radicals, and all can be measured during the desorption. Problem as well is that if you're only interested in the desorption of the intact molecule, the yield that has been found for methanol is extremely low as compared to the photodesorption yield, typical photodesorption yield you would find for more simple molecules. So, okay, this is the case of methanol, but there are many other organic molecules. So the question is, can we just make, do all the cones will behave like methanol? Is it really true? Is there some molecule which behave differently? How can we understand that? Of course, for that, we need more data. So what I will do now in the following is come back a bit on two relatively recent studies we made at the MONARIS. First of it is to investigate again the case of a pure CO ice with the aim to have ideas on the actual mechanism of the energy transfer which is in. Second is to try to extend our knowledge on the photodesorption of organic molecules. And I will present you some studies we made for formic acid, methyl formates, and acetonitrile. So let us begin with the case of the CO ice. And we want to have more information on mechanisms, microscopic mechanism of desorption. So we do so. In fact, what we will do, we will use laser-based technique. Why we will use laser? Because we will take advantage of the fact that we can do time-resolved measurements. So the idea is to shine VUV laser pulse, energy of which we can control or more or less control, and send it to the eyes. This pulse will trigger the desorption of the molecule. And the molecule will ionize resonantly by a multiphoton process. This is called the RAMP process, by a time-delayed UV pulse, from which we can control as well the energy, and we can as well control the time delay. And once the molecule is ionized, and we can easily detect the ion with a detector. So this looks like this. In fact, there are experiments which are extremely easy to do. We have the vacuum chamber, which is here. The ice is grown on a cold surface, which is here. And to generate the VUV pulse, we will need to make a third-order nonlinear effect in a rare gas cell in between two pulsed tunable lasers. One is visible, one is UV. And then once this is sent to the surface, the molecule is ejected, and you will have to ionize it with a third laser, and then you will have to detect it also with a temporal gate. So everything has to be synchronized. All the laser has to work at the same time, which is basically not happening, but sometimes it does. But still is a very powerful technique. So why do we do that exactly? First, with this kind of experiments, we can choose to fix a delay in between the desorbing pulse and the probe pulse. And with that, we will just change the energy of the ionizing photons. And with that, in fact, we will have access to the population of the internal or the rotational or vibrational levels typically of the ejected molecule before its ionization. And this will give us the internal energy distribution of the molecules. Second, you can fix this energy, and then we will vary the delay in between the desorbing pulse and the probe. And this will give us, in fact, the time of flight of the molecule between the surface to the place it is ionized. And that will give us information on the kinetic energy. So if we have both, we will have access to a full picture of the process. We know how much energy we put in. We know how much energy we get at the end. And that we can compare to molecular dynamic simulation from colleagues and try to be conclusive on the mechanism we are looking at. So this technique we tested on CO, and this is mostly a work which has been done by Romain Bazalgette, who finished his PhD in 2022, and Antoine, that you've already heard this morning. And this is originally a technique which has been sought by Jean-Luc, so this is a big work, a big part of the work which Joyce brought to the team. So what do? In the case of CO, we choose a VUV energy to go in this transition here for the condensed CO. And for the probe, we choose this transition in the gaseous CO. And in fact, we will probe the Q branch of this transition in the vibrational state 0,0 by ionization from excitation with 2 photons and ionization with a third one. So this is a 2+1 RAMP scheme. So what did we obtain with that? Well, first, these are experiments which were realized at a fixed delay in between desorption and probe, and we scan the photon energy. So normally we should be able to make this RAMP spectrum of the gas phase molecule. And as you can see, we can resolve a very nice Q branch of the gaseous molecules. And with this spectrum, in fact, we can simulate a RAMP spectrum using the PGopher software. And with the PGopher software, you can feed the population of each occupied rotational levels. And this will give us, in the end, the total rotational distribution of energy of the desorbed molecule. So this is an example here. So you see, this is the experimental spectrum, which is fitted by the black spectrum here. And at the end, you get here the rotational population of the molecule. So with that, we can have access to the full rotational distribution. We can also have access to the vibrational distribution. And I'm not showing you the data here, but in fact, most of the case for CO, molecules are ejected in the vibrational ground state. We can also do kinetic energy distribution measurements. To do that, we will freeze the energy of ionization, and we will vary the delay in between the ionization and the probe. And this will give you this kind of spectrum, which is the black trace here, which is a time of flight spectrum, which, if you want, you can compare to a Maxwell-Boltzmann fit, and you can see that it's everything but thermal, which was expected more or less. And from this time of flight, you can have access to the velocity distribution. From the velocity distribution, you get the kinetic energy distribution. And that you can do by ionizing low rotational level, average of rotational level, high rotational level, and this will give you this kind of distribution here. When you have the population fraction, which is here, and the kinetic energy distribution. So with this kind of data, what can we do? But in fact, we will compare with theoretical calculation, which are made in Lille in the laboratoire Flamme. And it's in the team of Maurice Monerville. And this is the PhD students who did most of the work concerning that. So what they do is they theoretically model a CO cluster, and then they simulate the excitation by putting all the photon excitation in a vibrational excited state of the electronic ground state. And then they will do the dynamics using ab initio molecular dynamics. And they let evolve everything. And this is what they obtain. So as you can see here, the excited molecule is the blue one. It's in the bulk. It's very high vibrational levels. And because of the high vibrational levels, it will begin to attract surrounding CO molecule, which falls on the excited molecule, and that you've got an impulsion transfer to the surface where the molecule is ejected. So maybe I can show it again. Yeah. So here you've got the excited molecule, and here it's a surrounding CO. At some point, the potential becomes attractive. The molecule falls on the excited molecule, and then you've got the energy transfer. So it's very nice because it's really explaining this indirect phenomenon. And what is nice as well with this theoretical calculation is that you can have access to the internal and kinetic energy of the ejected molecules. And with many, many trajectories, you can make some statistics. And if you compare to experiments, this is what you observe. Experiment data are dots, theoretical data are the bar graph. And you see that in vibration, translation, and rotation, we have a very good comparison, which in fact validates this mechanism. So to conclude on this concerted approach is quite powerful. It elucidated a mechanism which was in fact open for years. We knew that it was indirect in 2012. We had absolutely no clue how that was happening. And now we knew that. Now we know that. And of course, this open possibility knows not to study pure CO ice, but to put coadsorbate, vary the properties, and see how that changes with this mechanism. And this opened up a lot of future studies. Now, for some minutes I have left, I would like to come back to the case of organics molecules, the case of methylformate, HCOH, and CH3CN, and we did more classical photodesorption experiments. We make the ice of the organics either pure or mixed with water or with CO. We shine light from synchrotron beamline desir. We vary the photon energy, and as a function of photon energy, we detect the molecular flux of molecules which are ejected. Raw data looks like that typically. So one step is one photon energy. And with that, you can derive photodesorption yields. So what did we observe? I will begin with HCOH and HCOCH3. These are the data we obtained for photon energy at 10.5 eV only. And okay, this is relatively complicated to look at. Everything which is blue is with water. Everything which is red is with CO. Everything which is black is pure molecule. But one thing which is extremely striking is that we don't see at all the desorption of the intact molecule. We can only reach the upper limit there. Second thing that we see a collection of fragments for HCOH here or HCOCH3 here. All the fragments that we see are the product of direct photodissociation of the molecule. Also, the yields do not depend on the ice composition. This was extremely surprising. What does that mean? Well, if there is any indirect energy transfer, or if there is any photochemistry, there should be some photochemistry, it is not coupled to the desorption. And this is a very important fact. It's totally different than what we observe for simple molecules. And the absence of indirect energy transfer, you can also see by the wavelengths or the photon energy dependence. It is not changing at all whether you've got pure molecule, molecule mixed with water, molecule with CO. And that is a strong conclusion. It's in fact, to many, many aspects, these two molecules behave exactly like methanol. Almost no desorption of the intact molecule. A lot of fragments are ejected. Well, is it always true? Of course not. In the case of CH3CN, things are different. CH3CN is also dissociating. We also see fragments, but we also detect very well the desorption of the intact molecules. And this is very different. Also, if you change CH3CN, if you change the ice in which CH3CN is embedded, you will have you would expect some difference. And in fact, it's exactly like the same other organics. There is absolutely no difference, neither in yields nor in photon energy dependence, whether you take acetonitrile in water, in CO, or pure. Okay, for a modeler, it's really cool because you've got actually one value to consider. For us, it's more tricky to understand what's going on. So to conclude on the case of the organics, there seems to be different families of molecules. Some molecules are behaving like methanol. So that's kind of methanol-like one. Desorption of the intact molecule is really low. Fragmentation dominates a lot. But in the case of CH3CN, it's not the same. Desorption of intact molecule is as well efficient and compares very well to the desorption of fragments. Is it true for any oxygen-bearing molecule? Are they like methanol? Nitrile, isonitrile, are they like acetonitrile? But it's too early to say. We still miss a lot of data. Right now, this is the status of what is known concerning the photodesorption of organic molecules, and there's still a lot of work to do. So with that, I would like to finish. First, I would like to thank, of course, co-workers, especially co-workers of the group in MONARIS, but also in the framework of the INR Pixies, which is ending now in January and which helped us to do a lot of the experiments I've been showing you. PCMI, of course, Soleil, support from the region Île-de-France, and you for your attention.